12 billion light years away, there's a galaxy that isn't spinning. Astronomers pointed the James Webb Space Telescope at it, expecting to see what every young galaxy is supposed to show. Gas swirling inward, stars gathering momentum, the whole system turning like a slow cosmic pinwheel as it grows. Instead, they found stillness. Stars moving in every direction at once, canceling each other out. The signature of a galaxy that has already finished growing up, already stopped forming new stars, already behaving like something ancient. The problem is the timing. The light reaching that telescope left this galaxy when the universe itself was less than 2 billion years old, a small fraction of its current age. Full-grown, retired galaxies aren't supposed to exist yet at that point in cosmic history. This one does anyway. And it isn't the first thing James Webb has found that quietly breaks a rule astronomers were fairly sure the universe was following. The discovery comes from a team led by Ben Forrest, a research scientist at the University of California, Davis, published in May 2026 in the journal Nature Astronomy. The galaxy itself has a catalog name rather than anything poetic, XM-Vid1 2075. Forrest's team wasn't working blind. Years earlier, using the WM, Keck Observatory in Hawaii, as part of an ongoing survey called MAGAS-3N, short for Massive Ancient Galaxies at Z greater than 3, near infrared, and designed specifically to hunt for massive galaxies in the early universe, they had already confirmed two things about this object. It was one of the most massive galaxies known from that era, already carrying several times as many stars as our entire Milky Way, and it had already stopped forming new ones. That combination, big and finished, made it an obvious target for follow-up. What Webb added wasn't the discovery of the galaxy. It was the discovery of what the galaxy was doing, or rather what it wasn't doing at all. It's worth pausing on how unusual it is for a survey to catch a galaxy this early already in what astronomers call a quenched state, meaning it has essentially shut off star formation entirely. Most galaxies in the young universe are still actively building themselves, pulling in gas, igniting new stars, growing brighter and messier by the year. A galaxy that's already massive and already finished this early was rare enough on its own to earn a spot on the MAGAS-3 team's watch list years before Webb ever looked at its rotation. That's the state XMM-Vid1 2075 was already known to be in. What nobody expected was for its internal motion to look quite this old as well. To understand why not spinning is such a strange thing to find this early, it helps to think about how a figure skater pulls into a spin. Arms out, they turn slowly. ARMS in, they turn fast, because the same rotational energy gets concentrated into a smaller shape. Galaxies work on a similar principle during formation. As the gas and dust fall inward under gravity. Conservation of momentum naturally sets the whole structure spinning, the same way water spins as it drains from a bathtub. Current models of galaxy formation expect nearly every young galaxy to carry at least some of that spin, a leftover signature of how it assembled itself. Only much later, after billions of years of growth, mergers, and violent collisions with other galaxies, does that orderly rotation sometimes get scrambled into randomness, stars moving in every direction like a swarm instead of a coordinated wheel. That scrambled, non-rotating state is something astronomers see regularly in old, massive galaxies nearby, galaxies that have had 10 or 12 billion years to collide, merge, and settle into slow, directionless motion. Finding that same worn-out signature in a galaxy from the universe's toddler years is like meeting someone who looks decades older than their birth certificate says they should. Actually, measuring that motion from 12 billion light-years away is its own kind of feat, and it relies on the same physics behind a sound you've heard 1,000 times without thinking about it. When an ambulance races toward you, its siren sounds higher-pitched, and when it speeds away, the pitch drops, because sound waves bunch up in front of a moving source and stretch out behind it. Light does something almost identical. Material moving toward us gets its light waves compressed toward the blue end of the spectrum, while material moving away gets stretched toward the red end. If one side of a galaxy is rotating toward Earth while the other side rotates away, astronomers can detect that as a subtle color difference from one edge of the galaxy to the other. Forrest's team looked for exactly that pattern in XMM-Vid1 2075, and across the whole galaxy it simply wasn't there. No blue shifted side, no red shifted side, just stars scattered across a wide range of velocities in every direction, with no coordinated turning at all. The analogy has its limits, and it's worth being upfront about where it breaks down. A siren only ever moves in one direction at a time, so the pitch shift it produces is simple: higher approaching, lower departing. A galaxy is millions of stars, each on its own orbit, and the light astronomers collect is really the blended average signal from all of them at once. Untangling a genuine rotation pattern from that blend, at a distance of 12 billion light-years, where the galaxy itself appears as barely more than a smudge of pixels, requires extremely precise spectroscopy and painstaking modeling, not just a single-color comparison. That precision is exactly what the James Webb Space Telescope was built to deliver, and it's part of why this kind of measurement was essentially impossible for galaxies this distant before Webb existed. Ground-based telescopes like Keck are extraordinary instruments, but resolving the internal motion of a galaxy this small and this far away, rather than just its total brightness or overall mass, needed space-based infrared sensitivity that simply didn't exist until recently. The team didn't test this galaxy in isolation. Alongside XMM VID 2075, they examined two other massive galaxies from roughly the same era of cosmic history, and the contrast turned out to matter almost as much as the galaxy itself. One of the three showed clear, orderly rotation, the kind current models expect. The second showed a messier, irregular structure, not yet settled into any clean pattern. Only the third, XMN VID 2075, showed that flat, fully scrambled motion typically reserved for galaxies many billions of years older. This one in particular did not show any evidence of rotation, which was surprising and very interesting, Forrest said. Three galaxies, three completely different life stages, all existing at essentially the same moment in cosmic history, less than 2 billion years after the Big Bang. That spread alone tells you early galaxies weren't all following one tidy script. So, to recap what's been established so far, this is a galaxy that Keck Observatory data had already confirmed was unusually massive and no longer forming stars, seen at a point when the universe itself was still very young. James Webb's contribution was showing that its internal motion doesn't just look old on paper, it looks old in the most literal sense that astronomers can measure. Scrambled, directionless, indistinguishable from galaxies that have had 10 times as long to get that way. Two independent instruments, two independent lines of evidence, both pointing at the same conclusion. That raises an obvious next question. If galaxies are supposed to need billions of years of mergers and collisions to lose their spin, what happened to this one so fast? Forrest's team has a working answer, though they're careful to call it a hypothesis rather than a confirmed explanation. Rather than the slow accumulation of many small mergers over a long stretch of cosmic time, they suspect a single dramatic event. Two galaxies, each already spinning, colliding almost head-on while rotating in nearly opposite directions. If the timing and geometry line up, that kind of collision could cancel out the rotation of both galaxies almost instantly on cosmic timescales, leaving behind exactly the kind of directionless, scrambled system Webb detected. It's a bit like two spinning tops crashing into each other at just the right angle, each one's spin absorbed and canceled by the impact rather than continuing on its own. There's a hint supporting that idea sitting right in the image data itself. We see a large excess of light off to the side, Forrest noted, describing a bright patch that doesn't belong to the galaxy's main body, the kind of feature you'd expect if something else had recently slammed into the system and was still being digested. It isn't proof, it's a clue, sitting exactly where a smoking gun would be if the collision idea is right. If you're the kind of person who likes catching a mystery mid-investigation rather than after it's already solved, this is a good place to hit subscribe, because the trail on this one is still warm. It helps to step back and ask why any of this matters beyond one distant, oddly behaved galaxy. Galaxy rotation isn't a cosmetic detail. It's a direct fingerprint of a galaxy's entire assembly history, how much gas it pulled in, how violently it collided with its neighbors, how long ago its last major growth spurt happened. When astronomers build computer simulations of the universe, they're essentially trying to reproduce, statistically, how many galaxies should look calm and spinning versus scrambled and settled at every point in cosmic time. A single non-rotating galaxy this early doesn't demand a rewrite of those simulations by itself, but it does put a very specific, testable claim on the table. Current models say objects like this should be extraordinarily rare at this epoch. Now there's a real one, sitting in the data, daring someone to go find out just how rare actually is. This isn't the first time James Webb has handed cosmologists a galaxy that arrived looking more finished than the timeline allows. Since the telescope began science operations, astronomers have repeatedly found galaxies in the first several hundred million years after the Big Bang that appear far more massive, more structured, and more mature than standard models of galaxy formation predicted. A group researchers only half-jokingly started calling universe breakers. Under the standard cosmological model, small clumps of matter are supposed to merge gradually into bigger structures, over enormous stretches of time. Dark matter halos growing first, ordinary gas and stars gathering inside them only gradually afterward. Webb kept finding galaxies that seemed to have skipped several steps of that process entirely, assembling Milky Way-sized populations of stars while the universe was still in its infancy. In one especially striking case, a galaxy spotted at a distance corresponding to roughly 300 million years after the Big Bang appeared to already hold a stellar mass comparable to galaxies we see nearby today, a pace of growth that some cosmologists said should be essentially impossible under the standard timeline. Some of that mystery has since been narrowed down, and it's worth being honest about which part. Earlier this year, a separate team led by Katherine Chorowski at the University of Texas at Austin, working with NASA, showed that a meaningful chunk of those impossibly massive early galaxies weren't quite what they first appeared to be. Extremely bright, active supermassive black holes sitting at the centers of some of these are bigger and more massive than its actual star population justified, like judging a house's size by a floodlight left on in one window. Once that extra light gets accounted for, some of the most extreme universe breaker claims shrink back down to something standard models can actually explain. That resolution, though, doesn't reach every case, and XMM Vid1 2075 sits outside its reach entirely. Its mass wasn't estimated from a single Webb image easily confused by a bright black hole. It was measured years earlier from the ground, at Keck Observatory, using a completely different method, then treated as settled before Webb ever got involved. What Webb revealed wasn't a mass problem that black hole light could quietly explain away. It was a motion problem, a galaxy behaving like a senior citizen, while the universe itself was still a toddler, and no amount of reinterpreting its brightness changes how scrambled its stars are moving. The universe breaker puzzle isn't fully solved. It's been narrowed, unevenly, one galaxy at a time, and this one is still standing on the unsolved side of that line. There's a second layer to this that makes XMM Vid1 2075 harder to wave away than the black hole cases. Chorowski's team resolved a mass problem, essentially proving that some galaxies only look too big because part of what astronomers were measuring wasn't starlight at all. But XMM Vid1 2075 doesn't have a mass problem. Its size and stellar population were confirmed independently well before this controversy, using ground-based spectroscopy that doesn't share the same blind spot a bright, active black hole can create in Webb's imaging alone. Strip away every explanation that has successfully shrunk other impossible early galaxies back down to something ordinary. And this one is still standing there, fully grown and fully still, exactly where the standard timeline says nothing that mature should yet exist. Here's where the honest limits of this finding need to be laid out plainly, because a single galaxy, however strange, isn't the same as a broken cosmological model. And what's established, XMM Vid1 2075 is massive, no longer forming stars, and shows essentially no coordinated rotation, all confirmed through two independent methods, ground-based spectroscopy and Webb's own imaging. What's strongly suspected but not proven, a single major merger between two oppositely spinning galaxies, is the most likely explanation for how it got that way so quickly, supported by the odd excess of light seen off to one side. What remains genuinely unknown is how common this kind of object actually is. Some computer simulations of galaxy formation do predict that a small number of non-rotating galaxies should exist this early, but only rarely, almost as statistical outliers rather than an expected population. Whether XMM Vid1 2075 is one of those rare, already anticipated outliers, or an early sign that current models are underestimating how fast galaxies can grow up, isn't something one object can settle. Forrest's team is now actively searching for more examples specifically to answer that question, comparing whatever they find against the same simulations to see whether the numbers still line up. It's also worth saying plainly what this finding does not claim, because it's easy for a story like this to drift into implying more than the paper does. Nobody involved in this research has argued that the Big Bang model is wrong, that the age of the universe needs revising, or that some new exotic physics is required to explain a single slow-rotating galaxy. The claim is narrower and more disciplined than that. One object's measured motion doesn't fit comfortably into the timeline current models predict for objects of its kind, and that mismatch is worth chasing down with more data, not worth treating as a crisis on its own. That search matters more than it might sound like at first. Cosmology doesn't get overturned by a single strange object. It gets tested by patterns. If XMM Vid1 2075 turns out to be a one-off, an unusually dramatic collision that happened to occur unusually early, then it's a fascinating anomaly and nothing more, the kind of outlier every large enough dataset eventually produces. But if Webb keeps finding more of them, scrambled, mature-looking galaxies well before the standard timeline says that maturity should be possible, then the pattern itself becomes the discovery, not any individual galaxy. That's the real reason a single Nature Astronomy paper about one distant object is worth paying attention to. It isn't the headline, it's the first data point in a test that's still running. So, did James Webb find something that shouldn't be possible? By the strictest reading of current galaxy formation models, yes, at least provisionally. A massive, quenched, non-rotating galaxy has now been confirmed through two separate observational methods at a point in cosmic history when the standard timeline says that combination of traits should still be billions of years away. Nobody has proven the models are wrong. What's been proven is narrower and, in its own way, more interesting. At least one galaxy got old fast, likely through a single violent collision rather than the slow, patient process astronomers assumed was required. And nobody yet knows whether that's a fluke or the leading edge of a much bigger correction to how we think galaxies grow up. Picture that bright patch of extra light sitting just off to the side of the galaxy's main body again, the detail forest's team flagged as a possible clue. It's still there in the data, unexplained in full, waiting for someone to run the numbers on exactly what collided with what and when. That's usually how these stories actually end, not with a single triumphant reveal, but with one more thread left hanging, one more target added to the follow-up list. Somewhere out past that galaxy, further back toward the Big Bang than anyone had firmly measured stellar motion before, there may be more of these premature old-timers waiting to be found, each one either backing up the model we have or quietly chipping away at it. What makes that search worth watching isn't the promise of a single dramatic answer. It's the fact that the answer, whichever way it lands, will come from counting real objects rather than arguing over one. Right now, the universe has produced at least one galaxy that grew up far faster than the rulebook allows. And the honest answer to why is still being written, one Webb observation at a time. Tell me in the comments what convinces you more, the missing rotation itself, or that strange patch of extra light sitting just off to the side of it.